Hey everyone, welcome to this explainer. I am absolutely thrilled to have you here today. We're going to unpack one of the most fascinating and rapidly evolving frontiers in modern science, brain-computer interfaces, specifically focusing on Neuralink. We'll be demystifying the technology behind the headlines by diving deep into a comprehensive 2025 research paper published in the International Journal on Science and Technology by researcher Chaitanya Sahu. Whether you are deeply familiar with neurotech or just starting to follow the developments, our goal today is to cut through the noise and look directly at the data, the hardware, and the real-world human impact of this groundbreaking system.
Then we'll go inside the actual Neuralink system. After that, we'll see some real lives and real impact. Fourth, navigating the current limitations. And finally, the future of neurotechnology. All right, let's dive right into Section 1, the brain-computer divide, bridging the gap. 86 billion. Let that number sink in for a second. That is roughly the number of neurons firing away inside your brain right now. To put it into perspective, it's pretty much on par with the number of stars in our entire galaxy. It represents one of the most complex information processing systems known to science. Now, for decades, researchers have been chasing this incredible, ambitious goal of bridging the gap between all that dense biological neural activity and external digital technology. But as you can imagine, trying to tap into a network of 86 billion firing neurons? Yeah, that is a monumental engineering and medical challenge. To understand where we're going, we kind of have to look at where we've been. Early brain-computer interfaces, think the Utah array from the 70s and 90s, they were totally groundbreaking, but they were also incredibly constrained. We're talking bulky external hardware and transcutaneous wires. That means wires literally crossing right through a person's skin. Naturally, that tied users to labs and brought a really high risk of infection. Plus, the signals often degraded over time due to rigid materials. Neuralink's paradigm shift is a completely different ballgame. Their vision? A system that's fully implantable, entirely wireless, and cosmetically invisible once it heals. No bulky lab setups, and definitely no wires poking through the skin.
Moving right along to Section 2, inside the Neuralink system, the hardware and surgery.
At the absolute core of this whole system is what they call the link. Picture a fully implantable device about the size of a large coin. Tucked away inside this tiny little package is a custom-designed ASIC. That's an application-specific integrated circuit, which handles all the neurosignal acquisition, processing, and Bluetooth transmission. But the big takeaway you should grab here is really the practicality of its power management. The link runs on a lithium-ion battery that gives users about 12 hours of continuous wireless operation. And when it runs out, it can be fully recharged in just about an hour using a simple inductive charger you just place externally over the implant site.
Now, the 2025 research published in the IJSAT journal points out something super fundamental about how this device even came to be. Neuralink's crazy rapid progress wasn't just about, making a better battery or a faster chip. It was all about vertical integration. Instead of trying to source a bunch of disparate parts from different places, they built the whole shebang simultaneously. We're talking novel flexible materials, automated surgical techniques, miniaturized electronics, and the signal decoding algorithms, all developed under one roof in a single, seamless pipeline. And the most delicate part of that pipeline operates at a mind-boggling scale of 4 to 6 microns. For context, that is significantly thinner than a single human hair. The link actually connects to the brain using these ultra-thin, flexible polymer threads, each packed with dozens of electrodes. So why exactly does flexibility matter so much? Well, traditional rigid electrodes tend to cause tissue damage and inflammation, which inevitably degrades the signal. These microscopic threads, though, are designed to literally move with the natural pulsations of the brain tissue. This massive reduction in mechanical mismatch is absolutely crucial for keeping those neural signals crystal clear over time. But here's the catch. Human hands simply cannot insert thousands of microscopic, floppy threads into a brain with the precision needed to avoid catastrophic damage. Enter the R1 robot. It essentially acts as a highly advanced automated neurosurgical sewing machine. The process works in 3 steps. Step 1 involves creating a small opening in the skull. Step 2, the R1 robot uses micrometer precision to insert these threads directly into the motor cortex. It actually actively avoids blood vessels to minimize any bleeding or tissue damage. Then, step 3, the link device is placed completely flush with the surrounding skull bone and the scalp is closed right over it. Fast forward a few hours of surgery and the patient goes home with a totally invisible implant. Okay, let's look at what this actually means for people in Section 3. Real lives, real impact. The PRIME study.
9 bits per second. That is the actual information transfer rate users have achieved on Neuralink's telepathy software. To really put that into perspective for you, this rate roughly doubles the previous world record for brain-computer interfaces. What it basically means is that the system is translating neural activity from the motor cortex, that's the part of the brain that plans movement, and turning it into cursor movements and digital clicks. And it's doing this with a speed and fluidity that is actually starting to approach able-bodied individuals using standard mice or touchscreens. It's wild.
But honestly, the stats only tell half the story. The real proof is in the human lives changed. Take Nolan Arbog, a young man with quadriplegia from a spinal cord injury who became the very first recipient back in January 2024. He went from needing a caregiver to position a mouth-held stylus for him to independently browsing the web and gaming for up to 12 hours a day using nothing but his thoughts. Then we have Alex, a former designer. He's actually using the link to get back into creative work, manipulating complex CAD software and Adobe Illustrator. And perhaps the most powerful example is Brad, who has late-stage ALS. Brad had lost all voluntary movement except for his eyes, but his standard eye-tracking software completely failed him in bright sunlight. Well, the link doesn't care about lighting. It allowed Brad to communicate through an on-screen keyboard outside, which meant he could finally attend his son's robotics competition and present at his church. I mean, we are talking about life-changing digital independence here.
And this isn't just some fleeting trick that only works in a controlled lab. According to the data published in early 2025, across the study, participants have racked up over 670 days of implant time and 4,900 hours of actual system usage. But here's the really important part. Participants are averaging 6.5 hours of independent daily use. That specific metric is a massive benchmark for any assistive tech. It proves this system is reliable enough to just be woven seamlessly into everyday, unsupervised life.
But Neuralink's vision is pushing beyond just moving cursors on a screen. In 2025, they kicked off the Convoy study. Alex, who we just talked about, is cross-enrolled in this one. And he's been demonstrating the ability to use his neural implant to control an actual assistive robotic arm. Because the link provides such high-density signal quality, he can achieve precise, natural control over a physical robotic limb. We're talking tasks like basic object manipulation and even feeding himself. They are literally bridging the gap back to the physical world, which is just absolutely incredible.
Of course, it's not all perfect. Let's head into Section 4, Navigating the Current Limitations, the Unvarnished Realities. Let's look at a totally balanced ledger of where this technology stands today. On one hand, the successes are undeniable, right? High-density neural recording, amazing wireless daily independence, and highly adaptive decoding algorithms. But the challenges are just as real. For example, in Nolan Arbog's case, more than half of those microscopic electrode threads actually retracted from their initial positions in the brain, which temporarily degraded his system's performance. On top of that, proving the long-term durability of these signals over many years without needing to constantly replace the hardware is a major hurdle the company is actively trying to clear with newer device modifications. And let's zoom in on another major hurdle, recalibration. Early on in the Prime study, users were spending up to 45 minutes every single day just recalibrating the software so they could maintain accurate cursor control. Why? Because neural signals in the brain can naturally shift. This happens due to learning, neuroplasticity, or just the body's minor biological responses to the implant itself. However, Neuralink has been tackling this head-on using adaptive machine learning. Their software continuously refines its decoding models in the background while the user goes about their day. Because of that massive 45-minute daily disruption has reportedly been reduced down to just a few minutes. It's a fantastic example of real-world usage actively informing and improving the tech.
And that brings us to our final chapter, Section 5, The Future of Neurotechnology Beyond Motor Control.
Historically, navigating the FDA with novel neurotechnology is a long, arduous process. Yet, the velocity of regulatory achievements here is pretty hard to ignore. In May 2023, Neuralink got their initial investigational device exemption to kick off the Prime study. Then, in September 2024, they secured an FDA breakthrough device designation for blindsight, a project aimed at restoring vision. Fast forward to May 2025, and they locked in another breakthrough designation, this time for speech restoration. These designations don't just offer prioritized regulatory review. They validate that the FDA clearly sees the potential of this single platform to treat a wide variety of severe conditions.
Which brings us to those targeted future applications outlined in the source research. The BlindSight project actually intends to bypass damaged optic nerves entirely, stimulating the visual cortex directly using high-density electrodes. The speech restoration protocol? It aims to decode attempted speech movements straight from the brain's language centers, offering natural communication back to stroke or ALS patients. And looking even further down the road, researchers are noting potential treatments for epilepsy through highly precise seizure detection and maybe even cognitive assistance for things like dementia. But, as the 2025 IJSAT paper rightly points out, as this platform scales up to treat these different conditions, there has to be an ongoing rigorous emphasis on data privacy protocols and expanding clinical trials to fully prove out that long-term safety.
All of this leaves us with a truly profound question to ponder. Neuralink has proven that yes, we can safely and wirelessly connect the human brain to a digital interface, bringing actual science fiction into reality for patients with severe paralysis. But as this platform evolves to restore vision, to restore speech, and perhaps one day even augment memory or interact seamlessly with artificial intelligence, the line between what is biological and what is digital is permanently blurring. So what is the ultimate future of human cognition when our minds can speak directly to the machines we build? Thank you so much for joining me for this explainer. I really hope this deep dive helped structure your understanding of this absolutely incredible technology. Catch you next time.